equation, calculus, Taylor polynomials, infinite series, differential equation.
Well, welcome back, everybody, to another amazing edition of AP Calculus BC Live. Yesterday morning, Tony was talking about how we feel kind of like we're part of your family, right? That we're kind of like those crazy uncles, maybe. I don't know if I like that word, being crazy uncle, but it made me think about my job as an uncle. And I will tell you, in all of our family gatherings, and even if we're just with teacher friends or anybody that I know, I'm always the uncle or the guy that's, no matter where I am, trying to teach somebody calculus, right? I don't care if it's my grandmother, our English teacher at our high school, my nephews, my sister, wherever we are, dinners, family, whatever, it always comes up. I'm always trying to show them how cool calculus is. So maybe I am that uncle, right, Tony? Maybe I'm the guy who is teaching calculus, and maybe that's why I'm kind of like the uncle, and Tony's an uncle, because we're the uncles that are teaching calculus. So, but we are so glad that you're here today. Today, we're going to be talking about verbal interpretations, explanations, and reasoning, all connecting ideas with the A, B, and BC exam. As always, you can find our materials in the little link underneath the comments section of the video. It'll be nice, one folder there. You can download the problems that we're doing today, as well as seeing a whole bunch of other problems that you can practice with. And then each evening around 9 o'clock Eastern time, our friend Ted Gott will upload the first draft of the worked out solutions for you as well. So like I mentioned earlier, I am here with one of my great friends, Tony Record. So Tony, how are we doing this morning?
Doing great. We had a great meeting this morning with all the members of our production staff. All of our interns were in on this, and we've got so many exciting things scheduled for you. I don't think we could even mention them all in a 55-minute show. I really don't.
Yeah, I think it's one of those, it was an all hands on deck meeting. We had literally ones and ones of people that were joining in that meeting today. So it was really cool. And so before we do jump into our problems, we do want to mention a couple things about what's coming up next week, and then also talk a little bit more about the AP exam that's going to be coming up on May 12th, because we are getting pretty close to that, right? We're less than 2 weeks out. And so we're going to be spending all of next week. We're still going to be learning and some strategies and some content skills and some tips and reminders next week as well. But we're also going to be embedding a whole bunch of just things that you should know for the testing side of the exam this year. So we're going to be hitting a lot of that next week. But something probably even more exciting than all of that is we're going to be having a t-shirt giveaway next week. And Tony, tell us a little bit about the t-shirt design and the giveaway, and what we know now versus what we're going to share maybe later on tomorrow and next week.
Certainly. We have been hard at work on a design that really captures the essence of these last 5 weeks, and we think we're there. We think we've got something that you'll be really proud of, and so we're gonna print up several of these t-shirts, and they will be given away to our random audience members, to our students. And the only stipulation is that you do have to have a Twitter account. That would be the only way that you could acquire a t-shirt. So if you don't have a Twitter account, it's very easy to make one. And you might find later on in your professional life, sometimes having a Twitter account can be kind of nice in the professional world to an extent, more so maybe than Instagram, Snapchat. Mm-hmm. So if you've got a Twitter account, you're ready to go. If not, and you would like to get a t-shirt, think about doing that. And then we will make sure that any student that receives a t-shirt, their teacher will automatically get one as well. And the reason is because we can't ship these to the student per se, to the student's residence, but we can ship them either to the teacher's home or to the school. So make sure that you are communicating with your teacher so that they are aware of this as well. So teachers, you don't really have to do anything in terms of the contest. Let your students take care of it, and we'll get some t-shirts out to some very lucky winners to help commemorate this wonderful experience that we've shared together.
Yeah, I think the teacher is going to be, I don't want to oversell it, Tony, but it's going to be amazing enough, I think, that they're going to want to have a Twitter account or to make one if they don't already have one. So we'll share the details of how you could win a t-shirt every day next week. By the way, it's not just a one-time deal. Every day next week, we're going to have a random winner. And there'll be a couple of stipulations, like Tony mentioned, hoops that you might have to jump through in terms of we want to see some things about that you've followed the College Board's advanced placement channel on YouTube. If you're watching these videos, you're probably already following it, so you can find the videos quickly, and a couple other things like that. But no strings attached, just an awesome t-shirt to commemorate our time together. So that way, when we have our family dinner sometime in the future, we can all wear our t-shirts and camaraderie. So other things next week coming up. Tony, I'm excited about this. A good friend of ours is going to be joining us. We're going to have a guest speaker on Tuesday, Steve Kokoska, who is a former chief reader. So if you're a student, that might not mean anything to you, but the way the AP exam works is there has to be what we call a chief reader. The chief reader does several things, but the chief reader helps oversee the entire process of how we grade the exams. They make all the final decisions on what would earn a point, what wouldn't earn a point, and things like that. But they do a whole bunch of stuff leading up to the exam as well, helping piece together the exam. So Steve Kokoska, who's a professor at Bloomsburg University, is kind of the top of the hill in terms of knowledge about the exam. And he was going to be sharing with us a lot of student misconceptions, a lot of mistakes, common errors, some tips and strategies. And we're going to have a Q&A with Steve, and our students and teachers will have a chance, if they're watching live, to submit some Twitter questions during our session with him, to ask him questions, and we can bring those up during our work with Steve. And we've done a lot with Steve in the past, Tony, you and I have, and his presentations and his insights are incredible.
Yeah, truly one of my favorite people in all of higher education, and the history of the advanced placement calculus program has been really he's been phenomenal in what he's been able to do for teachers and students.
Yeah, we definitely don't want to miss that. That'll be next Tuesday. He's also been part of the test development committee. Again, a lot of fancy words, but what that means to you is there's a committee of a small committee of teachers and professors who write the free response questions. Like they develop the exam, the questions each year, and he's been on that committee, a vital part of that as his chief reader duties as well. So he's very familiar with how the questions look on an exam, kind of the background behind questions, why they're written a certain way, what to look out for, and things like that. And so I think he's not involved with the exam this year, so he's not going to in peril of sharing any insider information he's not allowed to share. But he can share some experiences as, hey, as a former chief reader, as a former test development committee person who's written questions, if we were under these circumstances, these might be some of the things that we would look at. It might be some strategies that we might use, we might have used, and when I was on there a couple of years back, to develop some of these question ideas. So I think his insights are going to be immensely helpful, and I'm very excited that he's going to be there with us. And don't forget, each day next week, we're going to be talking about the online portal from the College Board. We'll be making sure that you get all those links, your to-do list. We want to make sure every single student is confident, not just in the material, but confident in, I can use this online system. I'm not going to worry about the submission process, how it's going to work. And so we're going to emulate that next week, multiple different days. We'll have chances. We do practice problems on here. We'll give you time to do like a sample FRQ or parts of sample FRQs, and then upload your responses to make sure everything's working in the same testing system that the College Board is providing for students to kind of test things out. So we're really excited about that, and we're looking forward to it. So we hope that you'll join us each day next week, so that way we can make sure that you're ready for the exam, not just in terms of calculus content, but all those little factors that we don't want to be a barrier to your performance. So with that said, we're going to jump into it today, right? Verbal explanations, interpretations, reasoning, notation, all these things are kind of intertwined together. And we've talked a lot about content in the last couple of weeks. We've spent this week talking about problem types like tables or graphs or equations and kind of how they might look on this year's exam. And this today's topic may not seem like as enticing. Like, okay, it's verbal interpretations, like how important could that be? The problems are going to be tables and graphs and equations. This is a tiny piece of something, right? Well, I want to show you just how important this topic is before we jump into it, so you understand how valuable and how important this stuff is. Because it's not just about the content and what you know, it's about how you communicate that, explain that, and then show the readers of the exam that you understand what you're doing. And so this is what we call the course and exam description that College Board put out for teachers this year. And I feel bad, Tony, because they put all this time making this beautiful binder for the course exam description. They put it out this year, and a lot of it is not going to be valid this year because it's, we cut out some units, and so some things that aren't quite, they didn't get their full performance out of it this year. But there's two parts to the calculus course. There's what we call the content. Those are all the ideas and concepts that you learn. How do you take a derivative, the chain rule, use substitution, Euler's method, Taylor polynomials, right? That's kind of like the what of what you have to learn. But then there's the other side of it, which we call these mathematical practices. And that's going to be not just the what, but how can the College Board ask you questions about those ideas? What do they want you to be able to do with them, right? And so these 4 practices are sort of the ideas of how questions are written. So it's not just about the content, it's about these 4 ideas. And so there's only 4 of them. So all the questions on the exam deal with one of these 4 practices. So we have, implementing processes. That's a fancy way of saying, hey, can you do the chain rule properly? Can you take an integration properly? Connecting representations, can you understand how to work with tables and graphs and equations? That's what we've been spending this whole week on, right? Is connecting those ideas together. But look closely at practice 3 and 4, justifications, and then communication and notation. 2 of the 4 practices, 2 of the 4 ideas of how questions might be written on an AP exam are designed about giving you an opportunity as a student to justify or give reasons to your answers, and then to communicate using good notation, improper integrals, L'Hopital's rule, things like that, communicating properly, and then also using the right explanations, in your answers. So those 2 practices are 2 of the 4. And if we look at just the free response on a typical exam, right, on a full length exam, this is how they kind of break out the free response problems. That practice 3 and 4 will account on the free response somewhere between 46 and 79% of the exam. It's a pretty big range, but it goes from about half of the points on the free response to 3/4 of the points are just on those 2 practices. That's a really high weight, right, on the free response. And that's because practice 1 and 2 have a lot heavier weight on the multiple choice, because it's hard to do a lot of communication and notation on a free response question because we can't see, on a multiple choice question, because we can't see your notation. So we save a lot of that for the free response. Well, since this year's exam is only free response, certainly we can assume that at least as much of a percentage, right, is going to still be involving those 2 practices. So this is really an important lesson today. It's not so much about the content. We're going to still do some practice problems and do content, but we really want to focus and highlight the importance of that communication idea and how you can write things to guarantee or to ensure that you're going to get all the points that you deserve, right? And so there might be more than one way to do these problems. It's always, more than one way to explain something. So Tony and I will just be giving you some exemplars today, some models that we know would earn credit on a typical exam, right? Once you start deviating from that, there are some other things that are acceptable, that are equally correct, but sometimes some slight changes the meaning of what you've written down. And even though it's really close, it wouldn't quite earn a full credit on the exam. So our first problem, a nice table problem. When Mr. Passwater, hey, that's me, starts his live online help session for his AP Calculus students, there are 25 students already in the session. Between 0 and 10 minutes, students will enter the online sessions at a rate modeled by this function e prime of t, where e prime of t is differentiable and is decreasing, and e prime of t is measured in students per minute. Use the data in the table to approximate e double prime of 5, and then more importantly for our lesson today, using correct units, interpret the meaning of this in context of the problem. So first things first, when it comes to the actual calculus part, I don't want to breeze past this because it's still really important, but I'm going to assume at this point from all of our previous lessons that you're feeling pretty comfortable about how to do these ideas. So I'm not going to spend too much time on that beginning part, but to approximate e double prime of 5, and we have to approximate it because we only have a table of values, we're going to pick the 2 points on either side of that point, the closest points on each side. Sometimes students ask, well, why can't I pick just any 2 points on either side of it? When we approximate on the AP exam, we expect the best possible approximation, and in general, that's going to be by picking the 2 points closest to it on either side. So you would not get the credit for the approximation if you pick 0 and 10. We want to see that you pick the closest points to it. So we're going to get e double prime of 5 is going to be 3 minus 8 over 6 minus 4. That takes care of the approximation part, right? No need to simplify, leave it like that, we're good to go. Now the other part, using correct units, interpret the meaning of this. So my students have a hard time with units sometimes. And I tell them the easiest way to think about units is when you do a fraction like this, think about where those numbers 3 and 8 came from, right? Those units, 3 and 8, were students per minute. So this numerator, the 3 and the 8, I can just write that as next to the answer, students per minute, right? And the bottom 6 and 4, those values were just labeled in minutes. And so the units in the bottom are going to be minutes. A lot of times students want to cancel out those minutes, which they don't. You could actually leave your answer just like that. This would be a really nice, clean answer with correct units for the answer. If you wanted to reduce it, you could. It's the same thing as saying students per minute squared. Sometimes students will write something like that, students per minute squared or students per minute per minute. Any of those are equivalent as long as we're not canceling out those minutes. And then the last part, interpret the meaning of your answer in context of the problem. So now we're interpreting a derivative, aren't we? And so there's a lot of ways you could do this, but it's a little bit trickier, I think, when you're interpreting a second derivative, when you're interpreting the rate of a rate, because now we're not just taking a derivative, we're taking the derivative of something that is already a derivative or a rate. So we have to make sure we incorporate that into our answer. I recommend my students to just always start out when you're interpreting a derivative. I like to start out by using the phrase, the rate. I like to use that phrase right off the bat, okay? Also, I probably would backtrack one quick second, and I would incorporate what the question was asking for. So it wants me to interpret E double prime of 5. I would say E double prime of 5 is the rate. That way I've incorporated this into it. And the reason why I'm doing this is because I've already told them what E double prime of 5 is approximately equal to, right? So now I'm going to say E double prime of 5 is the rate of what, right? I think the easiest way to not sort of get lost in your words or say the word rate too many times. Sometimes students know there has to be like a rate of a rate, and then we end up getting a lot of derivative rules, right? Whenever I'm interpreting a second derivative, I always start out by saying it's the rate, and then it's the rate of what? It's what's derivative. And I know it's the rate or it's the derivative of E prime, right? E double prime is just the derivative of E prime. So it's the rate of E prime, but instead of writing E prime, because that would not be in context of the problem. I can't just say it's the derivative of E prime. I'm going to replace E prime with whatever E prime is in the problem. E double prime is the rate of E prime, and E prime, according to the question, says students enter the session at a rate of E prime. So what is E prime? Well, according to the problem, E prime is just the rate that students enter the session, right? That's what E prime is. So E double prime is the rate, right? That, or I'll say that might be a better word here. It's the rate of the rate that students enter the session. It seems a little bit weird with the wording. I think the wording is the toughest part because a lot of us are always wanting to make nice, English sounding sentences. Sometimes when you're doing a derivative of a derivative, it might sound a little bit bulky, but if we start out by saying the rate, and then we replace E prime as the rate that students enter the session, now we have it's the rate of the rate that students enter the session, and we have to include our units. And remember, our units would be in students, in this case, per minute over minutes, or however you wanted to simplify those units, right? And then we want to also tell it when at t equals, what was that, 5 minutes? So when we are trying to describe our derivative, remember Tony mentioned noun, units, time, right? So our noun it's the rate of the rate that students enter. That's our description. The units would be in students per minute, and then at t equals 5. It's important whenever we're trying to interpret a derivative, we always say the word at, right? It's always at a specific time. So those are a lot of elements. I think it's a lot easier to interpret a first derivative for students, but that second derivative, we've seen that a lot on recent exams, interpreting the rate of a rate and what that means in context. So that's going to be our initial problem. If we look at part B of this problem, this one's going to go a lot more quickly because we've been talking about this a little bit, but is there a time where E double prime is -2? Well, remember, we're given a table of E prime, and we're asking about E double prime. And whenever a question starts out as, is there a time, we know it's going to be one of those existence theorems, either IVT or MVT. And we can decide which one it is based off of, are they asking about what's given to us, or are they asking about the derivative of what's given? Since E double prime is the derivative of what's in the table, it would be an MVT type question. If this was asking about E prime, then it would have been IVT, because they're asking you about what they've given, right? IVT talks about what you've been given in the problem, and then MVT is asking about the derivative of what you've been given. So we've been given a derivative of the table, so we're going to be using MVT. And so the first step is to just go ahead, whenever you're doing IVT or MVT, is we want to always check the endpoints of the table. So E prime of 10 and E prime of 0, we want to know what those 2 points are. Well, E prime of 10 according to the table is 1, E prime of 0 is equal to 21. And then what are we going to do with that, right? Once we know the 2 endpoints, for mean value theorem, we know the mean value theorem says the instantaneous rate of change of a function is going to be equal to the average rate of change of that function on a closed interval at some point. So we're going to find the average rate of change of these 2 endpoints. And so we're going to get 21 minus 1 over 0 minus 10. And guess what? If you work that out, you get -2. The average rate of change of E prime is equal to -2. And the question is, well, does E double prime have to equal -2? Well, that's the conclusion of the mean value theorem. The mean value theorem says, if you have a function, the average rate of change, if you know that somewhere in there, there's going to be a derivative, an instantaneous rate of change with the same answer, as long as the function is continuous and differentiable, right? Don't forget those conditions. So we kind of showed some pre-work here. Typically on an exam, this is like worth 1 point for checking the average rate of change. And the second point is for a proper explanation. And for mean value theorem, I like to tell my kids, we have to make sure that the function we're using, E prime, has to be continuous and differentiable. Well, we know it is because it tells us in the problem that E prime is differentiable. So we're going to say, since E prime of t is continuous and differentiable, right? Remember, we have to say both. We can't just say differentiable. When you're doing a mean value theorem, you must include both of those pieces, right? Even though we know that differentiability implies continuity, we need to spell that out on our explanation. So since E prime is continuous and differentiable on the interval 0 to 10, the mean value theorem, we've already shown all the work that we need. We can go right to our conclusion. The mean value theorem guarantees, I like to use this template where we say, since our function is continuous and differentiable, the mean value theorem guarantees. And how do you want to phrase this? I tell my students, once we get to here, let's just repeat the question. Let's just use the exact wording from the problem so we don't mix anything up. We're just going to rephrase it so it's no longer a question. Instead of saying, is there a time, we'll say the mean value theorem guarantees there is a time, right? So we're going to use this exact wording. There is a time t, and notice I'm not even going to change a single part of this explanation because I want to just use their own words in my answer. There is a time t 0 less than t less than 10 such that E double prime of t equals -2. So there's a nice mean value theorem. So 2 good explanations. Those took a long time. The rest of them that we'll be doing will be a little bit quicker, at least my part of it. And then also for you, we're going to make a little document with all these kind of templates in there. They're not a template of you have to use this form, but it at least gives you a model of what would be a good approved response on a question like this. And so we're going to put all these together in a nice typed up document. We'll put it in the Dropbox for you. That way you have access to them later on. They're probably in the Dropbox sometime tomorrow. We're going to be combining a lot of these ideas together. So Tony's going to take us to a couple more pieces here before we jump into BC part 2.
Take a look at part C of the same question. We are now going to be asked to use correct units, explain the meaning of the definite integral from 0 to 10 of e prime of t with respect to t in the context of the problem, and use a right Riemann sum with the 4 subintervals indicated in the table to estimate that definite integral. And I think what I'm going to do is I'm going to actually answer the second half of this question first. So we're going to find this right Riemann sum. And so if I want to communicate, if I'd like to show some good notation, what I'm doing here is I'm trying to find this integration, this definite integral, and I know that it is indeed an approximation. So I can use these nice symbols, right? We see this word estimate, so I'm communicating effectively what it is I'm doing. And the right Riemann sum, we've done these a couple of times before. We've got 4 subintervals. We know that it's a right side. And so if we look at our table, we can see that as we move from one interval to the next, and so forth, we have those 4 nice subintervals. And as far as the width between these intervals is concerned, the difference between 0 and 1 is 1, 1 and 4 is 3, 4 and 6 is 2, 6 and 4 is 10. And that's very common. We've talked about that before, how the intervals, these subinterval widths, I should say, aren't necessarily going to be the same width. So we just have to do our length times height 4 separate times. Right Riemann sum indicates that we are very interested in these 4 numbers. These are the 4 values that we're going to make up the heights of each of these 4 rectangles. So there we go. We just assemble it. We have our first interval of width 1, height of 18. We continue that process. The second interval, 3 by 8 rectangle, followed by a 2 by 3, and then finally a 4 by 1. And I can't emphasize enough, you're probably tired of hearing me say that, but you really need to show a sum of products in order to receive the full credit for any type of Riemann sum approximation. If we were to add all of these together, 18 and 24 and 6 and 40, it's pretty simple to do. Of course, you wouldn't have to do that. The answer, I believe, here is I want to say this is 4 times 1 here, not 10, right? 4 times 1. That would really give Mr. Passwater a lot of students coming into his session. I'm sure he would love. So, and you know, that's actually a good thing here, because by adding these up, I do want to get a number. I want to get a value that we hope that makes sense, right? If we had like 2 or 3 as our answer, that wouldn't make a lot of sense. We've got certainly more students than that. But if we had like 1,000, that would be a pretty nice AP program. And maybe that's probably a little bit too on the long side of that. So sometimes adding those values, if it's very simple to do, can give you some kind of reasonable context whether the problem makes sense. So we have this wonderful, nice number 52 here. Now we have to answer, well, what does it mean? And that's where this explanation comes into play. So within the context of the problem, we're going to use this acronym that we've talked about quite a bit, this notion called NUT, right? Nouns or number, units, and then time. So as I assemble this, I would say, well, what do we have here? Well, we've got 52 of something, right? So we could say that there are 52. All right, now I'm kind of thinking units. You know, what does this 52 mean? This 52 is an amount of something. And in this case, it would be awesome calculus students, just like yourselves. Okay, well, what are these calculus students doing? Well, it looks like they are entering an online session. And then we want to make sure that we address, well, when are they doing that? And because we are interpreting a definite integral, it's very important that we use a word that will link itself to a time interval. In part A, I believe Brian used the word at. At's a very important word when you're interpreting the meaning of a derivative at a point, because it's a specific moment in time, right? One specific moment, at. But when you're talking about an interval of time, you might want to think about using some other prepositions, from, over, during, throughout. Any of those would be acceptable. In this particular case, I'm just going to use the word from and to, right? So I say from time t equals 0. We want to make sure that we label that in minutes. We can abbreviate. And we will end at t equal 10 minutes. And we should have all of the elements of our nut there. And I've kind of color coded this so that you can see. So my n, the noun number, I can think of that as 52. Now, we could also kind of throw in the context around that entering, right? Adding the online session just gives the more flavor to the explanation. It's probably not 100% necessary, but it is nice to throw in there. And the units, I think the students kind of falls in line more with the units. And of course, these minutes here are going to be very important. And then the time aspect would be delineated by those orange highlighted features. So you want to make sure that whether you use NUT or some other acronym that your teacher has probably shared with you, you want to make sure that you have all of those elements in your explanation. And thinking back on my experience as a reader and reading several interpretation problems, whether it was derivatives or integrals, it seems like to me the most common element that is omitted is this T. Right? Students kind of neglect the importance of that aspect of the interpretation. So make sure that you include it. Now for part D of this problem, it asks us to think back, reflect back on that approximation that we just did and answer whether or not we have an overestimate or an underestimate of that definite integral. And of course, we have to give a reason. Underestimates and overestimates are tied to a couple of different things, solutions to differential equations, which we've talked a little bit about before. But in this case, we're talking about approximations of Riemann sums. And so it's very important that we understand that you need to delineate whether or not it's the feature dealing with increasing, decreasing, or the feature that deals with concavity. And in this case, it's determined by the increasing or decreasing behavior of our function. So it says up here in the stem that E prime, our wonderful E prime expression, is decreasing. So visually, I guess what that would look like is some kind of a curve that might look like this. And as you piece together these Riemann sums and cap them off on the right side, you can see that we are going to have areas of rectangles that aren't quite occupying the entire area underneath that curve. And a lot of times I'll have many of my students over the past 30 years that I've taught need to actually draw that picture because they don't trust themselves on just memorizing, decreasing, underestimate, increasing, overestimate, because it really depends on what kind of Riemann sum you're going to use. A left endpoint Riemann sum has just the opposite effect with an increasing, decreasing function. So don't feel bad about drawing a little picture off to the side to help you. Now, I will tell you that picture wouldn't earn credit, right? Any kind of graph that you might draw, a number line that you might draw will never earn credit, but it can be a very valuable tool for you to use to make sure that you answer the question correctly. So we're going to say in this particular problem that our integration from 0 to 10 of E prime of t that gave us this approximation of 52 is an underestimate. Now you'll notice we have not stated why. We have not given the reason. We have this picture, right? We might know, you might know as a student what the reasoning is, but you have to communicate that to the reader. And you just simply use the idea that E prime of t is decreasing. Now, it might be a good idea to be very thorough with this because E prime of t, who knows how long E prime of t is going to decrease. You know, maybe we get to a point where Brian's session's really good. After that 10-minute mark, he gets a bunch of kids that come in. Maybe they've been texting and saying, hey, you got to join this, man. He's doing some really cool stuff. So we might want to say that this E prime of t is decreasing on the interval 0 to 10. And Brian, I'm sure that would happen. I'm sure after 10 minutes, you're going to have that big influx of kids wanting to come in and catch more of your wonderful teaching. So that takes care of that takes care of our part C and D. Part Part E is something that we're going to leave for you. It uses the idea of a tangent line and approximation, but it also connects the idea of asking whether or not you have an overestimate or an underestimate, and that's that communication piece. So certainly check that problem out, and you can always check it with the key when it's posted later. Boy, BC2's got a lot of great things on this, and I think Brian's going to pick apart a few of the highlights of that. So Brian?
Sure. And Tony, this is going to sound awkward, but I'm going to make you stop sharing your screen for a second because I can't share my screen right now until you stop yours. I think I'm
Oh my
no
goodness.
longer a co-host. So
so I have control right here.
you do
Jeez,
have utter control. This is now the Tony show. Hey, there we go. All right. And that was right before, this is again flying by the seat of our pants, sometimes me more than Tony, but right before we started our session, we were on early this morning, like we are every morning. We get up pretty early, and around 7:30, Tony and I have another morning meeting together, kind of going through the problems and the ordering and how we want to do this, predicting how long it'll take us to get through each problem, which we've never ever come on time. We never learn our lesson. And then meeting with our college board producer, Sarah, and doing stuff. Well, at 8:58 this morning, 2 minutes before we went live, I logged out and logged back in. I can't remember why now, but it's something real quick. And I think I lost my co-hosting duties when I did that. So we're going to take a look at another problem here, BC number 2, and we're going to now switch to a graphical problem, right? So we did a table problem and kind of some of the explanations that might come along with that. Now we're going to look at a graphical problem and some of the explanations that might come with that and some of your interpretations. And so this is going to go in line with what we did earlier this week in terms of content, but we're going to focus on how do we explain our reasons or interpret some ideas. So here, another function, no longer in a context, not a real world situation, just a graph of f is given on the table or given above. And it's got a couple line segments and a semicircle, and then it introduces this other function g, where g is the integral from 4 to x of f. And remember, I said what I tell my students to do, when they ever have a stem where it has a function defined by an integral, the first thing I have them do, I said, I don't even want them to read the problem. I just want them to get comfortable, like I have something I could do right off the bat, is we're going to go ahead and take the derivative of this equation, right? We're going to go ahead and differentiate both sides, and we're going to get g prime on the left. That's going to be g's derivative. And then using that fundamental theorem of calculus, we're going to get a nice little f of x right there, right? We're just going to substitute that variable in, multiply by the chain rule. Well, x's derivative is 1, so we don't have to worry about that. And I also said I have them do it twice, right? So we're going to differentiate our new equation and get g double prime equals f prime. And we do that because we're probably going to be using that multiple times throughout the problem. But by making this connection, number one, I know that f is g. This is a graph of g. But you're going to see kind of some neat, easy ways to explain some of these. And this is where you're going to see some definite differences on how different teachers share about how they want students to explain their reasoning. And there's multiple correct approaches. So I don't want to make it sound like the other approaches aren't correct. I just want to show you something that maybe you haven't seen before that sometimes makes these interpretations a little bit quicker and easier and less mistake prone, right? And so here it says find all the values where the function g has a local maximum. So remember the other day I said I always have my students do this in terms of isolation, like don't try to find an answer right now. Just interpret what they're asking for. If g has a local maximum, what does that mean? Well, if g has a local maximum, that's because g prime, right? The only way to have a local maximum is if the derivative changes signs, right? It has to change sign from positive to negative, right? So that's what a local maximum would be. So then I can just kind of go about finding those answers. And so we have also like an entry point, like a blueprint or a roadmap. So again, before I try to find the answer, I want to think about how I would get to that point. So in order to figure out if something changes signs, my students, we know, we look for two options. Number one, we want to know if g prime has to equal 0 or undefined first. The only way for there to be a sign change is if the function was 0 or undefined. And then that's the locations where you might have a sign change. And then once we have that, we're going to look for a sign change, right? That's what we're kind of doing. So this is kind of our roadmap to finding relative minimums or relative maximums, either one. So the first step, where is g prime 0? Well, this is a graph of g, right? So I want to know, this is not a graph of g, this is a graph of g prime, isn't it? I hope you guys caught that. right? I wrote up here G prime equals F. Then up here I wrote F equals G, which doesn't make any sense, right? F is equal to G prime. So I want to know when G prime is 0. Well, this is a graph of G prime, and I can see this graph is 0 here, here, and here. Now, I'm not going to include the 12 because the question says between -3 and 12. It doesn't include those two numbers, so 12 really wouldn't count. But these are my three possibilities, right, to have a relative minimum or a relative maximum. And we want to figure out not just when the graph of G prime equals 0, we want to know when G prime, the graph, changes from a positive value to a negative value. Well, at -2, it's switching from a negative to a positive. At 4, it's going from a positive to a negative. And then at 8, we're going from negative values to negative values. And so this is the only location where we switch from positive to negative values. And so we can say at x equals 4 is our answer. And remember in the beginning how we said G prime changes sign, like how I interpreted that question first? Well, guess what? That is your justification. That is going to be your explanation. So we can just say, because G prime changes sign from positive to negative. And so some of my students are pretty astute, and what they've started doing was when they start writing that first step down about interpreting the problem, they'll kind of put it a little bit lower in the answer. So when they put their answer on top of it, they've already got their explanation already attached to it. And they then don't have to rewrite it. They just kind of put that part below and they say right before add x equals 4 because, and they have their answer all in one time. So they've almost created their justification or their explanation first before trying to find the answer, because when you do that, it helps give you a clear idea on paper of what you're looking for. So you don't accidentally look on the graph and find the wrong value. So I want to address one thing real quick, because sometimes we're told you have to use what was given to you in the problem in your explanation. And you certainly could talk about the graph of f. We could have said at x equals 4 because f changes sign from positive to negative. That's what the graph was given, right? So why am I allowed to talk about g when a graph of f was given? That's why this first step here is so critical. In the beginning, if we differentiate this function twice, we've already made these connections. We said G prime is F and G double prime is F prime. Once we've made those connections, I can talk about G or F, either one, as long as they're correct in my explanation. By making those connections now, I can immediately look at this question and then come up with the explanation without even having to worry about what the graph looks like. I know when I see the phrase G has a local maximum, that means that G prime must have changed signs from positive to negative. And then I can go back and look to figure out where that happens. We're going to try one more part here. We're going to do part C. I'm going to skip part B. We're going to look at part C just briefly. And I went ahead and rewrote that G prime and that G double prime explanation there. But now we want to figure out where G has a point of inflection. And so I want to share a quick document that I share. I'll put this in the Dropbox, but I give it to my students. And it's just a little PDF that talks about all these ideas: relative mins, relative maximums, increasing, decreasing, kind of those phrases we see a lot in the questions, point of inflection, concavity, things like that. And it tells them, okay, when they see a question like that, what's the possible entry point? Like, what do you look for first, right, to kind of get your foot in the door? And then once we have our answer, what's a proper or acceptable explanation or reasoning for your answer, right? And so we'll make sure we share that with you, but it's kind of a nice thing to have in handy. That way, if you have as a reference sheet, if you just want to double check yourself during the test, you kind of have that there. So G has a point of inflection. Well, according to my sheet, our starting point means we're going to first look when G double prime is 0 or undefined, right? Those are the possible places where it might happen. That's not going to guarantee it's going to happen, but they're possible places. But more importantly, our explanation is going to be because G double prime changes signs. You cannot have a point of inflection unless the second derivative of the function you're asking about has a change in sign. And so remember, this graph here was G prime. We want to know when G double prime. Well, this is a graph of G prime. We're now talking about the derivative of this graph. So I want to know when this graph's derivative is either 0 or undefined. Well, this graph has a derivative of 0 or undefined every time we see kind of a corner or a horizontal tangent. We've got 4 different locations where G double prime is undefined or 0. undefined, these corner points, and the slope of 0 here at the bottom of the circle. And we want to know of those, which ones do we see a sign change in G double prime, where the slope is changing? Well, we see a positive slope and a negative slope, and then a positive slope and a negative slope and a positive slope. So a whole bunch of sign changes, right? So it's going to end up being at all of those locations, right? At x equals 0, at x equals 6, at x equals 8, and then again at x equals 10. We have 4 different locations where the slope change signs. And then our explanation, when we go to our explanation, this entry point, that step number 1, the entry point, I tell my students, don't include that in your explanation. That's not necessary for your reasoning. That just kind of gives you an idea of where to look to find the possible answers. Really, the second step, which determines there's a point of inflection, that's going to be our reason. So we're going to say at 0, 6, 8, and 10, because G double prime changes sign, like that. Again, we can make a similar argument that involves F prime, because remember, G double prime is F prime. You can make an argument about that as well. But I just like to, if we make these connections early, we can do all this just by looking at the function that's given, kind of in isolation, and then get kind of a setup and an answer before we even begin to look at the information in the graph, which I kind of like that approach, but there's two different methods that will work, and either one of them is going to be acceptable. Tony's going to take a look at another example that's the same graph, but now looking at it in a particle motion context. Tony, what you got?
Yeah, at least we're going to kind of introduce this. But I tell you what, Brian, I've got this crazy idea. I want to see what you think about this. Because we're getting pretty close on time, tomorrow's lesson is going to be about putting this all together. And it was our intention to maybe talk a little bit about the last few of these free response questions and kind of let them bleed over into tomorrow.
Yep.
I'm saying that we hold off on that. We can really do a good job with this tomorrow. We'll share that template with everybody. And we're going to let you out of class a little early today, at least early for us.
That's a great idea, Tony. Let's do that. So how about tomorrow? We'll kick off tomorrow's lesson with this BC3, because this is actually very similar to the problems that we were going to have tomorrow. So instead of having a brand new question tomorrow, we'll do this because it's a really good application, I think, of derivative stuff, right, and integration stuff in the context of particle motion. And that's always a nice, easily testable idea. Since the exam is hoping to make this calculator non-required, there wouldn't be an advantage for calculators. Some of those uglier rate in, rate out problems may not be noticeable that we've seen in years past, but a particle motion with the graph would be a really good, I think, problem that could be easily tested this year. So
yep, sounds great. And Brian, I'm going to stop share. I'm going to throw it back to you so you can go to the tweets here. But as he's doing that, we want to make sure that you are aware that we'll probably only have the key posted through BC2 for today's session, so that we don't have the BC3, 4, and 5 out there floating around before tomorrow's session. But we promise we'll make sure that that key gets posted probably late in the evening, Friday, early Saturday morning. So it will be out there for you eventually. So
awesome. Well, walk us through some tweets, Tony. Tweets with Tony. Here we go.
That. Yeah, tweets with Tony. One of my favorite parts. So what do we got here? Well, we have got for our AP Teachers Rock, my calc teacher of the past 3 years, Mrs. O'Rourke. She's been preparing us all very well for the AP test with each of the FRQs and the circuits that she posts for us every day. That was sent by Theo, and Theo's from Massac High School in Monroe, Connecticut, which I believe is outside of Bridgeport, if I'm not mistaken. And for our AP Students Rock, we are so proud of these BC Calculus students at Incarnate Word Academy in Corpus Christi, Texas. Because of their continued hard work and determination, they are going to wreck the AP Calculus exam on May 12th. This picture was just so wonderful because it was a group of kids, and unfortunately we can't share pictures of students or their students' names, but it was this awesome picture with Wreck-It Ralph in the back, and so obviously their theme is Wreck-It Ralph. So I'm pretty sure that the students at Incarnate Word Academy are going to wreck the AP Calculus BC exam. So we want you to keep sending these tweets in, and of course we also want to make sure, if you are recognizing some students or a teacher, mention your school, right? Mention your town, because we want to make sure that we recognize those wonderful schools out there that are doing such a great job of teaching students, especially in this very difficult time.
And really, Tony just likes to challenge his atlas abilities. Like, when we go on a road trip, Tony's the guy that would still have a paper map and study it, not because he doesn't know where he's going. He just likes to know every city in the world.
I
So
do.
it's a challenge for him to see if you can stump him. So definitely keep sending those in. Tag Tony and I both, and then we'll get your tweets on there. Appreciate your teacher, appreciate your students, and then maybe stump Tony. We'll find out. Like we mentioned, exam information. We're going to go over a lot of this next week in depth. Next week's all about our primary focus is the exam itself, the platform, all that kind of stuff, in the context of doing some BC problems as well. Tony mentioned it, putting it all together, right? Tomorrow's gonna be putting it all together. We're gonna see some like more comprehensive free response questions. We're gonna write some free response problems that might be like a good simulation for this year's exam. So there might be a graph and a table combined, all these ideas, verbal interpretations. It's kind of putting everything we've done together in a almost like a simulated mock exam format, Tony. Is that what you call it?
I think so. I think it's going to set the stage for next week perfectly.
Awesome. And don't forget t-shirts, right? People are already calling in right now for Tony to say, hey, how do I get a t-shirt, right? They want to know how to get these shirts. The calls are going off the hook right now, but next week we're going to announce all of the information, and then tomorrow live on the air, Tony is going to share our t-shirt design. We're going to be showing you what is at stake here, right? So literally prizes worth thousands and thousands and thousands of micro pennies. So it's gonna be a pretty exciting time. So, but that'll be tomorrow, the live reveal of the shirt that you can win, not just for you, but for your teacher as well, for joining us during all these days and putting up with us every day. Pets of the day, Tony. We've got a couple of pets. So here on the right-hand corner, we've got Linus and Heather. I want to thank Erin for sharing her awesome dogs. They seem pretty excited. And then I had to share one of my own students' cats. This is my student, Will, in my own Calc BC class. He has two cats, Ace and Felix, and he sent me these pictures, and he said to me, he said, Ace, this is what she looks like in the morning when she hears our calculus intro theme song.
Ooh, I like it.
It's so catchy, isn't it? And Sarah, our producer, even mentioned a while back how she caught herself kind of humming or singing that song in the kitchen one day because she hears it every morning. It kind of just sticks in your head there. So she's like, man, I'm starting to sing calculus songs. She has to start reevaluating things and where her life is headed. I think we might have her as a convert to a BC calculus person. So this is Ace before these sessions. And this is Felix after the sessions, full of knowledge and a little bit glossy-eyed, right? Sometimes I'm sure you guys, we cover so much information some of these days, it might feel like, man, I don't know what's going on. So this is his fat cat, Felix, he calls him, post our BK Calculus live session. So Tony, remind us, who's our guest speaker next week?
Our guest speaker is the incomparable Dr. Stephen Kokoska, I should say, wonderful professor at Bloomsburg University in Pennsylvania. Lots of great insight. I really look forward to that.
Yeah, he's an amazing, not just professor and teacher and leader, but he relates so well to teachers and students, right? He's not how I imagine that college professor sometimes that we think about. He's just so understandable. He really understands the exam as a person who's written questions, who's led the exam reading and everything else. So this is going to be a can't miss opportunity. Tony, did I miss anything today? Besides,
I think we've covered it. Yeah.
Besides making you lose your whole BC3 problem today.
That's okay.
Stop.
I'll bounce back tomorrow. I'm okay with that.
Tony will lead off tomorrow and we'll be even better. But this is a record, 9:53, Tony. Well done today.
All right. You too.
All right. We're going to be taken out here with our friend Anthony with our typical AP Calculus outro music. See you tomorrow.
Stay safe, Ed. Keep learning.
AP Calc, yes, AP Calc. Welcome here to AP Calc, yes, AP Calc.